Okay, let's get started here. So today we continue with cluster analysis. We will also talk about project number 2. Are there any questions? Okay, so with respect to cluster analysis, we've talked about hierarchical methods, in particular, I guess a subclass of them called agglomerative methods. We introduced probably about 4 or 5 different methods last time. And so today we're going to talk about how we can choose then the number of clusters. Because remember, with these methods, we go from having n clusters down to 1 cluster. But we want something in between in the end. So we'll talk about how to make that decision. And also we'll look at, well, do these clusters make sense? Okay, so in order to choose the number of clusters, we need to first talk about, well, what would be a good cluster, what would be potentially a bad cluster. And so we have this simple plot here where we have just 2 variables, x1 and x2. And in the upper left-hand corner, we have what I would call a good cluster. Notice how all those points, whoops, let me do that. Notice how all those points are nicely close to one another, meaning that they're similar. The distances between those points will be relatively small. Then on the right-hand side here, we have potentially maybe a bad cluster, where we have 2 distinct, let's say, sets of points here. But they have been, I guess, I've drawn a line around them to say, well, maybe this is a cluster itself. Now, relative to x1, we see these points are similar to one another. But relative to x2, they are not, because we have this big distance here. So typically in some kind of clustering process that you use, you're going to get to a point that looks like this, where now I've drawn lines, dotted lines around what might be a more natural set of clusters, so that we would actually have 3 clusters. And so you often will get to a point like this. Now, before we get to this point, rather than having 3 clusters, imagine if we have 4 clusters, 5 clusters, 6 clusters, the way that these hierarchical methods work. The distances that you're going to have when you go from, let's say, 6 to 5 clusters, or 5 to 4 clusters, is going to be relatively small. So perhaps, for example, maybe when we had 4 clusters, we might have had something that looked like that. And if I were to look at the distance between, let's say, this cluster and this cluster, the distance would be relatively small. But let's say, again, we get to this point where we have these 3 clusters. To make a decision about, well, should this here go with that cluster, or should that go with that cluster, do you think the distance is going to be large or small? It's going to be large, relatively to everything that we've done previously. And so this is a very, very, very key point here, is that the distance to make a decision about what's going to be put together next, that distance or that similarity is going to be large relative to your previous distances that you've used to join clusters together. That is a key point. Once you see something like that happen, and I'm going to repeat myself, where the distance is large relative to what you've been doing before in terms of joining clusters, once you see that happen, then you might be thinking, uh-oh, maybe I don't really have 2 clusters here. Maybe instead I should have 3. And essentially you say, okay, I'm going to stop. I'm going to go with 3 clusters. That is the kind of logic that we're going to use to make a decision about how many clusters we should use. Hopefully that seems intuitive to you, because I think in the end it is. And we can, you can easily, diagram this out in 2 dimensions. But again, what happens if you have, let's say, 5 variables, 10 variables, 20 variables, 100 variables? You still make that same
you still go through that same thought process. While you're not going to be able to see it like this, you can compare distances that are found during your hierarchical clustering process. And when you see a large distance relatively to what you've been doing in the past, that should be a warning message to you that, okay, maybe I've gone too far. And I should actually, in this case, work with 3 clusters. Here's another graphical example with 2 variables. So again, you can see that we have a nice cluster here. And everything seems kind of similar to one another. People would refer to this as a compact cluster. It's rather, if you think of it this way, the radius is about the same throughout the cluster. It's a good cluster. This is a set of bad clusters here. And hopefully it's obvious. You would normally think that one point that's in the yellow there should be with the, it's hard, at least on my screen, I have a purple cluster and I have a yellow cluster. At least from my angle here, it's hard to see. You would think that this point here should be with those other points. That's what you would think. But an actual clustering method might come up with something like this. This is an example of a bad cluster. Or you might even go away and say, what cluster can do something like that? Well, think of what furthest neighbor does. The furthest neighbor method defines the distance between clusters as essentially, let me do this. Let's look at this part first. So maybe I got to this point here, and I'm going to need to make a decision about which clusters to join next, and it's probably going to center on that little point there, this cluster that has just one observation in it. And if you think of furthest neighbor, and its way of defining the distance between clusters, that distance would be between this point and this point. That would make a decision about should that point go to the upper left-hand corner cluster, that looks like a purple cluster on my screen. And also this point compared to this point in terms of distance. Those distances relatively, at least I was trying to draw it this way, are about the same distance. And so if this distance here was just a little bit smaller, then we would have something like this. Which isn't, just from looking at it in 2 dimensions here, it doesn't look like it's a good choice. But that's what can happen with furthest neighbor. Now, again, let's think of it in terms of distances before we got to this situation. Before we get to that situation, relatively the distances or the similarities should be relatively small. Then when we get to a process where we have this remaining, now we have a distance that seems to be much larger than what we would have probably had before. And so because of that, that might make you think, okay, wait a second, maybe I should stop the clustering process and actually end up with 4 clusters. Now, in the end, that's not ideal, because we can see, I think all of you agree with me, this is probably the way it should be. But this is also a nice little illustration about how some of these clustering methods don't always give you results that necessarily always make sense. This is why we look at typically more than one clustering method. That's why they exist, I should say. Some clustering methods might work well in some situations, some might work well in other situations. And so that's why it's often good to try out multiple clustering methods. Okay. Any questions about that? So, distances between, let's say, successive, iterations of the clustering algorithm are very, very important to us. That helps us make a decision about when I should stop the clustering process instead of going all the way to just having one cluster. And so there is a nice plot that we can use called a hierarchical tree diagram that allows us to see it. So this first diagram, the first example of it, is for that example where we just have 4 observations. And from this plot alone, we're not going to be able to make a judgment about how many clusters we should have for observations. I mean, you shouldn't do clustering analysis if you only have 4 observations. It was just a very convenient, very, very small data set to help illustrate the process of clustering. And so my purpose here of showing you this diagram for this data is just so that you understand what's actually being represented. Now, when I was going through my notes yesterday morning to prepare for this class, I was taking a look at this diagram here, and I was like, I think I could do a little bit better. And so I put together a new diagram. If you want to actually download this diagram, it's simply available on my course website. Under cluster analysis, it's this PowerPoint file here. I just chose to draw it this way, basically kind of reverse the way it was drawn, because this is the way that R is going to draw it. Different software packages will draw these kinds of diagrams in a different way. And for some reason, I chose something that was different than what R did. Okay, so this is what the plot looks like. So we can see we have on the left side a measure of distance. This distance represents, when I'm joining these clusters together, what is, according to the cluster analysis method, what was the distance between successive clusters that we're joining. On the x-axis, what we see are actual observation numbers. So maybe I should even put that there. Observation number. Okay. Now, if we go back, we'll look at nearest neighbor again. Go back to when we first looked at this. Let's see here.
Do a little bit of erasing. I saw the problem from last time. I'll just ignore the writing that I put on there. So we have these 4 different observations here. When we use the nearest neighbor method, remember we start off with 4 clusters. The clusters that are first joined are the clusters that have the smallest distance between one another. Since each observation is a cluster, that smallest distance is just the smallest distance between observations, and it will be that 2.24. So 3 and 4 were joined together first. Now, in order to decide which clusters are joined next, then we look at the minimum distance between clusters, and we looked at a table such as this. And we saw that the minimum distance was the distance between observation 1 and the cluster that had 3 and 4 in it. And so that will be joined next. So I have 1, 3, and 4. And then, of course, at the very end, then I join 2 to that 1, 3, 4 cluster. Okay. And had a distance of 2.56. So those distances now are actually shown in this plot. So again, remember 3 and 4 were joined first. And so the way that this is drawn is that we need to show that we have a connection between 3 and 4. And so that's why you see these lines connected like this that connect 3 and 4. Notice it's drawn out to 2.24, which was the distance between those clusters, or in this case, observations. Okay. Next, remember, 1 was joined to 3 and 4. And so we can see that indeed, here's 1. It's drawn out to 2.44, and it's joined then to what we had for 3 and 4. And then lastly, you can see how 2 is joined to the other ones. So this is a hierarchical tree diagram. It kind of gives you a history of the clustering process. It also shows you the distances. Typically on these plots, you will not see this written out like that. I just did that there for emphasis. Okay. So let's actually take a look at a little bit larger data set, still small, to help us understand what's going on here. It's simply also just two variables. This will also give us some experience with how you can approach the process in R. So the main function that people use in R to do these hierarchical clustering methods is what's called H-clust. H for hierarchical, clust for clustering. Okay? Now, in order to use this function, we actually have to do some stuff beforehand. First, remember how we typically always use standardized data. So we're going to need to use the scale function to standardize our observations. Second, we need to find all pairwise distances between the observations. We did this before. This was with the dist function. Then the results that you get from that dist function, all these pairwise distances, that's what you basically put as the first argument for H-clusts. So let's take a look at how this works when we actually use the nearest neighbor method. Remember, there's another name for it called single linkage. That's going to pop up here. So let me actually just jump on over here to R. So here's my data. And for some reason, I didn't actually display it, I don't think, in the notes. So we have simply 14 observations. The variables are called x1 and x2. I could do a plot of my data, and here it is. So we definitely see some differences amongst these observations, but just again, remember we're going to actually be using the standardized values. So to standardize, remember, we use the scale function, so I'm going to put that into an object called z, for the lack of a better name, and there we go. Let's actually plot then the corresponding data, just using the plot function for a scatter plot, then using the text function to identify corresponding observations. And this is what we get. Okay? Again, we see some differences there. So once I got my data, then I need to use the dist function to find all pairwise distances between the observations. So how this works, dist, first argument's x, equal, put in your data, the method equals Euclidean. So I'm using a Euclidean distance with standardized data. Then to something called dist.mat. And we can see here we have all these distances. So now imagine if you have a very large data set, thousands of observations, maybe millions of observations. Finding all these pairwise differences could be quite time consuming. And so later in the cluster analysis section, we won't get to it today, we'll look at other methods that avoid the need to find all pairwise distances, which can be very helpful when you have large data sets. Okay. Now, H-clusts, D for distance, that's the first argument. I put in my distance matrix, and the method for cluster analysis I want to use, nearest neighbor, also known as single linkage. So R happens to use this alternative name. So I'm going to put the results into clust.nn, nn for nearest neighbor, and then we're going to just print off clust.nn. This is what we get. In the end, it's not very descriptive at all, not very helpful to us. But there is a lot of stuff that's actually stored in there. So clust.nn is actually a list type of object in R. And so to see the components of the list, as we've done many times before, we say names clust.nn, and now we can see the stuff that's actually stored inside there. And in particular, if we do clust.nn $merge, we get now the entire history of the clustering process. Let me jump back over here to Word. Okay. What this is saying is false. I start off with 14 clusters for the 14 observations. And observations 13 and 14 are joined together first. That's why you see 13 and 14 there. And if I actually look up at the plot, notice how this makes sense. 13 and 14 were joined together first. So that's my first set of clusters. And R will actually refer to this as cluster 1. Yeah, just from looking at that, that looks like that's probably about the smallest distance between the 2 points, between any 2 points. So now I have 13 clusters, and R needs to decide, well, what do I join next? And what it decides to do is actually join observations 1 and 2 next. So come here. So this is my second cluster that was joined. Again, that looks reasonable in terms of distances, what we can see. And then next is going to join observation 3 with cluster number 2. So notice we have some numerical values have a negative out in front, and some have nothing out in front. Whenever you see a negative there, that's R's way of saying this is an observation number. Whenever you see nothing out in front of that number, that means this 2 corresponds to cluster 2. So now I can keep on drawing my lines here, and that's cluster number 3. And that, again, seems to make sense. Remember how R is making a decision about what the distance is between cluster 2 and observation 3. It's using the nearest neighbor, so it's taking this point and it's finding the distance. Furthest neighbor would take 1 and 3, find that distance. But we're using nearest neighbor here. And so on your own, I do urge you to do this, or I recommend that you do this. Actually keep on going through here. Well, let's join next. Let's join next. And actually draw it on the plot so that you can see the process, so that you can see, yeah, that makes sense about what's actually occurring here. Next, we can look at the height component of clus.nn, and this actually gives you the standardized Euclidean distance. So to do the 13 and 14, when that was formed, that was at a distance of 0.1346. So why is this called height instead of distance? Well, when we actually show it on one of these hierarchical tree diagrams, how high the joinings are shown corresponds to distance. And so for some reason, height is used rather than distance as the name of the component. So notice also between observation 1 and 2, it happens to have exactly the same distance.
What is the scale of the distance? It's just the scale that...
It would just simply be Euclidean distance between the actual observations. So simply, if you look at one of these plots, and if you have a ruler that was appropriately scaled to what these axes are, it would be the ruler distance. Okay. So, I did the plot the normal way, so you can take a look at that. Okay. Now, whenever you're approaching approach using a new function in R, I showed you how it's always good to use the names function with it so you can see what's actually stored inside of it. You should also use the class function so you can see what is the class of the corresponding object, and it just so happens to have the exact same name as the function name. It doesn't have to. In general applications are, but very often programmers will make that decision and do that. And so if I did methods class equal h
Unfortunately, this is an old version of what would have happened when for a previous class that I taught a few years ago. What it looks like now is what it looks like here. And we can see that we have a few different generic functions that we can use with the results from each cluster. We will focus typically on just this plot function here, because when I use plot with the results from each cluster, this is when I get my hierarchical tree diagram, or what R calls a cluster dendrogram. That's not the standard name.
Let me make this a little bit bigger. And so on the y-axis, R calls it height. This is what I was referring to before as distance. On the x-axis, we have the observation number. And so remember what was joined together first, 13 and 14. So we see 13 and 14 here. It was at a distance of 0.13, I believe. Yeah, 0.1346. And so essentially what R does to do this plot, it extracts these distances, these heights. It also extracts what's in merge, and then uses that to create the plot. Now notice that these numbers that you see here are not in numerical order. And the reason being is because, it depends upon where the observations are on the plot. If it wouldn't make sense to put, let's say, the way that I drew the plot, so the numbers were often near each other. But it nicely tries to arrange it so that you don't have lines going all over the place, and so that observations are close together. They're going to be joined together more quickly in the process. So the numbers are just arranged so that these observations are going to be close together on that x-axis. Yes.
So here, depending on this plot, so we can say that we have two big clusters, or we just go with the small ones.
Yeah, and so that's what you're getting at. You're foreshadowing where I was going. So yeah, thank you. And so what we see, so again, remember, we're looking at when the distances between clusters, when a distance is, let's say, much bigger than relatively what the distances were before. And so we can see that when I go from, let's say, two clusters, so maybe I have this here. When I have two clusters, now that distance becomes really, really big. In fact, let me draw it a different way. So I'm looking at this distance. Relatively to what we had before, that's huge. And so because of that, I probably want to stop with just two clusters. And if we go back here, now, let me make that smaller. That should make sense. What we see here is perhaps two clusters. So, let me come back here. I'm going to make this bigger again. So what people often do when they look at one of these plots, and you can see how this is kind of a little bit of a judgment call, because there's other possibilities for the number of clusters too in this case. But what people will do is once one of these plots are drawn, is that they'll look to see, where do I see these large distances? Where do they pop up? And we can see from going from 2 to 1 cluster, we see that distance. So what people will do is typically somewhere on the y-axis, and it doesn't really matter where, they'll just simply draw a line across there. Maybe even we'll label it with how many clusters. Notice how that horizontal line that I draw intersected the branches, you could say, of the tree twice. I have 2 clusters. Now, there are potentially other places where I could draw that line too that would make sense. So, for example, look at, this is going to be, actually, I'm going to just draw like a little dotted line over here. It's meant to be a horizontal line, even though it's not. So look at when I do this connection here between 1, 2, 3, and 4 and 5. Compare that to when I made the connection between 11, 13, 14, 10, 11, 12. Look at this distance here. So this is in succession. Remember, we're doing this in a hierarchical manner. I would connect these two, and then the next set of connections was between these two clusters. And so that's what I'm looking at in terms of the distances between successive joining of clusters. I am not, oops. Where was I? There we go. I am not focusing on this distance. Because this distance here is larger relative to what I have been doing. I would draw a line across, and that would correspond to, let's see, 1, 2, 3, 4 clusters. Because of the number of times that horizontal line intersects the branches of the tree. Now let's look at what that would look like here. We'll do some erasing. That would be this. So let me just double check that. Yeah. I would have these 4 clusters. And again, that makes some sense relative to what we see in this plot. And once again, in other applications, you're typically going to have many more variables in this. And so you're not going to be able to see this in this particular kind of a plot. Instead, you will have to rely on the tree diagram alone. And so this makes some sense to use 4 clusters. Now, let's see here. So look what was joined next and after that. Essentially, it was these points. In other words, let me do this. These are joined next. Relative to cluster analysis, that makes sense for those to be joined next. Those seem to be kind of the closest of the remaining ones. But perhaps that's just going too far. So we do see some separation there. But also you can see here again that this is somewhat, there's probably more than one answer here. And so like on a test or a project, I want you to justify your choice eventually at some point where you're going to have to actually choose the number of clusters. And you go to that hierarchical tree diagram, and that's how you make that choice. Now, shortly you're going to see some other methods that I'm going to use as well to justify the number of clusters too. But you start off with that tree diagram, you can say, I can see 2 and 4 clusters are justified because the distances between successive hierarchical joinings, we see a jump in it. We see it, if it's relative to what we've done before, we see some differences. Now notice here, I am not, let me do a different color here since it's not, I am not drawing a line right there. Because we can see that that distance there is actually even smaller than the previous distance that we just had when we were trying to choose the number of clusters. That distance is smaller. So no, I'm not going to draw my line there and say that I have 3 clusters for this particular method. Now,
Now, some other method might say, yes, 3 clusters is justified, but not for this method. So just to emphasize, again, because this is sometimes where students get mixed up. When I was making that decision about using 4 clusters, I was not looking at that distance.
I was looking at this distance. Even though they were for different areas of that
Tree diagram. I'm looking at successive joinings. So you can see that I like to draw those, well, anybody who's doing this likes to draw those vertical lines. And so there's an easy way that you can do that in R, is just to use the AB line function. The H argument means horizontal line. And basically you just need to draw the horizontal line at a particular location. In this case I chose 0.4, I chose 1. That would intersect the tree diagram in the correct spot. So I could have simply chose maybe 1.2. I could have done that. I could have chose 0.9. The key is it just needs to be somewhere between here and here for this one there. Line type equal dash. I use a dash line to help differentiate it from the solid lines that you see on the plot already for the diagram, and also line width of 2 to make it stand out. Now there's also some functions that are available to help you see which observations are in which cluster. This is going to be very helpful for us when we do some other plots. And we can use a function called cut tree. Notice it's actually spelled CU tree, but it's meant to mean I am cutting the tree. In other words, I am simply drawing one of those lines. I am cutting the tree. I don't know why it's not C-U-T and then T-R-E-E, but I'm just going to pronounce it as it is, cut tree. And so what I can do for the argument tree is put in the results from each cluster. And then say, where do I want to cut the tree out? Where do I want that line to be at? Let's say F1. And then what's going to be returned is that all the observations are going to be given a cluster number. So actually observations 1 through 8 are in cluster 1. Observations 9 through 14 are in cluster 2. I can also use cut tree this way, where if I use a K argument, that shows how many clusters do I want. So if I choose 4 clusters, then we can see like observations 1 through 3 are in cluster 1. I can form then a data frame with this information so that I can actually see the observations with their corresponding cluster number. And then this can be very helpful then to actually do a plot. So I do a scatter plot where I have the plotting character, so the PCH argument, corresponds to these clusters. Now I've chosen to work with the 4 cluster set. And also if I use COL for color, R automatically designates particular numbers with a set of colors, up to 8 different colors. And so color 1 is black, color 2 is a reddish color, color 3 is a greenish color, and so on, so that when I say col equal plus 4, which are numbers in there, I have different colors for the different clusters. And so now you can see this is what those clusters look like when I have 4 clusters. Everything is uniquely identified, or not uniquely identified, the clusters are uniquely identified by color and plotting point. There's also a function called rect.hclus. Rect stands for rectangle. And this is going to help me with my hierarchical tree diagram identify the different clusters. So if I say, after I've actually drawn a hierarchical tree diagram, I use this function and say tree equal, beginning the results from each cluster. I want 4 clusters, and I want to draw like a rectangle in red around the actual clusters. What's returned to me is, again, the different clusters, and what's actually automatically drawn on the plot is a rectangle around those clusters, just to help you see it. Okay. Well, what if I chose to use some other clustering method? Would I get the same results? And the answer is actually no. And very frequently in actual application, it's going to be no. So let's say I want to use the furthest neighbor method. Remember, another name for it is complete linkage, and R uses this other name to represent the actual method of H class. So again, H class, my distance matrix method equal complete. I put the results into clus.fn, fn standing for furthest neighbor. I can put it all in a data frame so that I can see the actual merging process. I can see the actual distances, the heights for these clusters. And so we can see once again that R first puts together observations 13 and 14. Next it does 1 and 2. But now we have a change from what we have with nearest neighbor, where before 1, 2, and 3 were joined together. Now we have 10 and 12 joined together. Let's look at one of these plots. Run the plot of the data to see if it makes sense. Again, 13 and 14 is cluster 1. 1 and 2 is cluster 2. And now I forget what was joined next. 10 and 12. 10 and 12 is joined. Oops, it should be 3rd. Okay? Yeah. I guess it makes sense. I mean, again, think about what furthest neighbor means. You know, nearest neighbor joined 3 with 1 and 2. But now we can see how with furthest neighbor, that distance between the 1, 2 cluster and 3 has greatly grown. Because now I'm looking at this distance here. That's bigger than what it was for 2 and 3. Okay. So I can do the hierarchical tree diagram, and this is what I get. Notice 2 clusters make sense again, but now 3 clusters make sense. To emphasize my point, because again, this is a place where students often make a mistake. When I chose 3 clusters here, I was not looking at this distance here. I was not looking at that. Rather, what I was looking at is the distance between successive joinings. Oops. So I was looking at here to here. That's what I'm looking at. That distance seems to be larger than what we've just recently had, much larger, kind of much larger, yeah. What we just recently had during this hierarchical clustering process. So in other words, when I say what we just had, I'm looking at these distances. Definitely for 2, that makes sense. You know, to go from 3 to 4 clusters, yeah, it's not as big of a distance as what we see from going from 3 to 2, but it is larger. Notice how 4 clusters would not make sense here. Because if I were to draw a line going across, there's only a little bit of a change in distances there. So 4 would not make sense in this particular case. So what are the 3 clusters? Let's see here. we'll just go to this diagram here. Oh, no.
Those are the three clusters. And again, it makes some sense to choose that. Well, what if I use the average method? Remember what the average method does? Let's say if you have two clusters, you need to find how similar they are, or in other words, the distance between them. What it does, it looks at, let's say if I have 5 observations here, 5 observations here in the different clusters, it looks at 25 different distances, all pairwise distances that could happen between these observations, and it simply averages those distances. And that's then the distance between this cluster and this cluster. And so in this particular case, when I use the average method, again, we start off the same way, and actually even the third step is exactly the same as what we had with furthest neighbor. Here's my hierarchical tree diagram. Once again, 2 clusters and 3 clusters make sense. Perhaps also, let's see, this would be 1, 2, 3, 4, 5. 5 clusters might make sense as well. Now you might be also wondering, why are all these numbers, let's say, at the same level on that x-axis? Why aren't they just drawn that way? And the reason why R does that is it's trying to avoid the overlapping of the numbers. Because if I had, let's say, 100 observations, you would have 100 numbers there. And so that's why it would actually, let's say, try to draw them up or down in that plot. Okay. Now, when you use the centroid method, this is something very odd. I haven't seen this in other software packages before. When you give the distances in each cluster, the distances need to be squared. Okay, let me look at my program here. So in other words, all you need to do, it is correct on the web. All you need to do is when you use the centroid method, well, you just specify centroid, but you need to give it a set of distances that are squared. So if I just simply take dis.mat, square it, caret sign 2, this is what's going to get me. Now why? So as I say, it's a quirk, computational quirk. And I don't like quirks in software. I like it to be intuitive and stuff, or if something needs to be done, it should just be done automatically. And I was looking into this a little bit more yesterday, and here's why. I should have had this in there before in the notes. It's simply because, remember what the centroid method does. The distances between 2 clusters is calculated as follows. Let's say if I have 5 observations here, I find the average of all these 5 observations. I find the average then of, let's say, another cluster here that's 5 observations, find the average of all these observations, and then I find the distances between the averages. This is different from the average method, but obviously there's some similarities in the terminology. But now let's say I had 5 observations here and I have 1 observation here, and I decided to join these 2 clusters together. Now I have a cluster that has 6 observations. Now I need to find a new center. So I'm going to have to compute the mean of all 6 observations again. And so as you go through the clustering process, you're going to have to continuously update where that center of that cluster is by continuing to use the average. And I haven't looked into the exact detail, but there is an actual computational formula that's used that helps make this process easier in terms of computational time. And for some reason, it requires square distances. if you actually want to see the actual computational process, and I've tried to look, this H-class function calls a Fortran program that you can actually look at that implements this process. I don't speak Fortran, so I haven't looked at it in depth. Okay. Now, I haven't really seen it actually explained in like other books and stuff before either. Now, as I mentioned, that there is a actual package out there called cluster that some people use. You're not responsible for it in this class. And people, rather than, let's say, using H-class like we've been doing, they use a function called Agnes. And this just gives you some information about that. Perhaps I don't need it in the notes, but I have it there still. So let's take a look at now the goblet data and do clusters with that, because that was some of the ultimate goals of these researchers, that they want to have natural groupings of these different goblets. We're going to look at this with respect to the nearest neighbor method. So we're going to also use standardized Euclidean distance. This is one of the few times where just plain old Euclidean distance with the actual original observations could make sense. It would be justifiable. We are going to focus on standardized Euclidean distance. So I read in my data. I adjust for the overall height of the goblets, is what we've done before. I then find my standardized values, is what we've done before, put it into an object called Z for the lack of a better name. And then next, I use the dist function to find all pairwise distances between observations, where I say method equal Euclidean. I use H-class with that distance matrix, and I say method equals single for the nearest neighbor method. And then I summarize everything in a nice little data frame here. And so what this means is that when R starts the clustering process, observations 3 and 16 are joined first. The distance between those two observations is 0.40. I can do then a plot, a hierarchical tree diagram of the clustering processes, and this is what I get. And so you can see here, I have drawn 3 different lines to designate what potential places to, let's say, cut the tree would be. So we can see for the highest line, highest horizontal line there, that corresponds to 3 clusters. And so I should have a plot of the data coming up. Oh, okay. Yeah, we'll get to that later. So I have 3 clusters there. So 23 and 24 is in one cluster. 4, 5, and 17, those goblets are in another one. And all the other ones are in the 3rd cluster. Now I also drew a line corresponding to, if I were to extend this down, this would be 1, 2, 3, 4, 5, 6 clusters. You have to be careful there because, again, since R is trying to avoid the overlapping of these numbers there, I still need to account for it. Well, this would be a separate cluster, this would be a separate cluster. Typically, this is not ideal to have a cluster with only one observation in it. So that's something to think about. Would we really want to use 6 clusters in this particular case? And then also we have a case where we have, let's say, 1, 2, 3, 4, 5, 6, 7, 8 clusters as well. And so to make these judgments about where I drew the line, and this is a judgment, I think it's obvious why I chose 3. Why didn't I choose 2 clusters? Why didn't I choose 2? Why is 3 preferred over 2? the distance. Notice when I go from 3 to 2, I look at this distance there. That distance is smaller than when I went from 4 to 3. So that's why it makes sense to draw the line at 3, not at 2. And so that's the kind of, and since there can be multiple choices here. But when I, let's say, grade you on a test, if you were to draw the line at 2, I would count off. Because that is not justifiable in comparison to 3.
Can you explain the tree line? The one, the first one.
I'm sorry, this line here?
Oh, how do you decide that with the distances?
Yeah, I mean, I was just looking at the plot there. I'm looking at these distances from, let's say, going from 5 to 4 clusters, 4 to 3 clusters, going from 3 to 2 clusters. And I saw that. Well, this seems, relative to what we've had before, relatively larger. And what I mean by before, I'm looking at 4 to 3, 5 to 4, 4 to 3, 5 to 4, 6 to 5, and so on. And so when I saw that distance was relatively larger, that's why I thought, okay, that would be a good place to draw the line at. I mean, look at the distance between, let's see here. So if I went from, let's say, so this is from going from 4 to 3. If I went from 5 to 4, I'm looking at that very small distance there. And so it would not make sense to draw the line there.
So, for example, if you go from 6 to 5, the distance would increase, so would decrease. So someone may say that I stop at 6, but we don't see it at, we should continue even with decrease. We see the decrease from 6 to 5 until...
Well, maybe we need to back up a little bit. So when I go from 7 to 6, we see that distance there is relatively large compared to what I was having previously. Then when I went from 6 to 5, which is what you're getting at, we saw the distance actually went down. The relative, I should talk about the change in the distance. Okay, that would be a better way to put it. We see that distance goes down, so that's why using 5 clusters would not be justifiable.
Okay.
I'm looking for jumps in these distances, where the jumps are, let's say, relatively much bigger than what we've had previously.
Okay, so my question, I should say that, so why we choose 6 over 3? Why we choose 3 over 6?
Okay, I'm sorry. From this plot alone, I don't think it is, well, let me back up. Think of it in terms of distances alone in those jumps. It's not necessarily one will be preferred over the other. Now, when I also look at this plot, I see that if I had 6 clusters, 23, 24, 18, and 2 would all be in clusters of size 1. Then that calls into question, okay, do I really want to do that? A cluster of just one observation. Think of it from the perspective of these researchers. I have this one goblet that's quite different from all the rest, so I'm just going to put it in its own little grouping. I also have these 3 other clusters that are all quite different from the rest, so I'm going to put them in each of their own groupings. That kind of defeats the purpose of, let's say, finding clusters that are similar to one another. So that would be let's say, a negative towards choosing 6 clusters. And also the same thing happens with 8 clusters here too. We're going to shortly take a look at another plot that helps us as well to make a judgment of, should I go from 6 to 3, or should I just use 3? I'm sorry, should I use 6 or should I use 3? I should put it that way, okay? So stay tuned. Any other questions about this diagram? Well, what if, let's see, so again, we can use some of these other functions, like, for example, rec.hclust, and if I say 6 clusters, we can see how everything is actually kind of diagrammed out for you. And this is something that can be very helpful. So, previously we used principal component analysis to kind of come up with an informal way to group the observations. You can also use principal component analysis as a way to justify your choice for clusters. In the previous example where we had 14 observations and we had 2 variables, we could simply draw, let's say, x1 on the x-axis, x2 on the y-axis, and we could see graphically, okay, yeah, that makes sense to join 13 and 14 together. But we can't do that here because now we have 5 variables. But what you can do is look at this using principal component analysis. If you have, let's say, 2 or 3 principal components that explain most of the variability in your data, then that should be just as good as in the case where we had just 2 variables and we looked at a 2-dimensional representation. With that principal component analysis, you could use a scatter plot, you could of 2-dimensional scatter plot, you could use a 3-dimensional scatter plot. And then you can use that to make a judgment. Okay, yeah, I see these observations are close together, so that makes sense to put them in one cluster. And so that's what we're going to do next. I've written a function called pca.ca.plot to help you in this process. You do need to take a look at it, look at the contents of it. It's just basically taking what we did with principal component analysis and combine it with cluster analysis. Take a look at that function on your own. We will look at how to run the function next. Okay. Let me do some stuff here. Okay, so to run this function then, I first specify where my data is. My data is in goblet 2. This function will automatically find the standardized values. I'm sorry, let me back up a second. I just specify where my data is, just the variables themselves. So notice how I have a -1 there. That first column was the observation numbers. And so what's going to do is take goblet 2, the remaining variables in there, and it's going to use principal component analysis using the correlation matrix, in other words, working with the standardized variables in the covariance matrix. My cluster results are stored in clust.nn. This is what I got from hclust. How many clusters do I want to actually show on my plots of these principal component scores? How about 3 clusters? I put a nice little title on it, and also I want to label the points. Okay, and so we get 2 plots, and this is just what's in my notes here, so I'm just going to go to this. Actually, we get 3 plots, excuse me. Let's see here. There we go. So the plot on the left, the plotting point corresponds to a cluster. So for what R calls cluster 1, based upon what hclust gives us, that's going to be plotting character 1, which is just an open circle, if you remember that from the intro to our notes. For what R calls cluster number 2, the plotting character is going to be plotting character number 2, and it's going to be what R refers to as a triangle. And so we can see here, here are the clusters. Now remember with principal component analysis we had, I don't remember off the top of my head, it was like 87% of the total variability explained by two principal components. And so, yeah, that makes some sense, what we see here. Let's look at let's look at with the third principal component, represented by the bubble. That's what's the plot on the right. And you might be thinking, okay, wait a second, 18 is with this cluster over there? Is that really something that should be done? Well, take a look at this. Look at this third principal component, how bubble is. It's a large bubble. So it kind of makes sense for that to be joined together with 3, 16, 7, and so on. This makes sense here. This makes sense here as well. You might wonder, well, wait a second. Look at some of those bubbles there relative to. Excuse me. Let me just make sure I got this right. Okay, yeah. So okay, yeah, that's what I did. Yeah, sorry, I just had to remember what I did before. So you see red and blue bubbles. Red corresponds to bubbles that have a third principal component that are positive. Blue ones are negative. Sorry about that. And so we see, well, we do have some division here. So that's kind of interesting. But I'm putting them into the same cluster. Well, this third principal component is actually explaining much variability of the data. So maybe that's not that big of a deal. And let's take a look at this in 3D. So we can see here's that 4, 5, and 17. Okay, that makes sense. Now note that these axes are scaled to be exactly the same length. So by doing the bubble plot the way I did, sometimes that can distort stuff because that third principal component is definitely not as meaningful as the first and the second. And so what we can see here, here's 23 and 24. But take a look at this large set of these large points that are in black. Okay, maybe that seems a lot more reasonable than what we saw in that bubble plot, that they should all be joined together rather than necessarily separated. Again, think of it in terms of that, what would be like the z-axis for a three-dimensional plot, which is representing principal component score number 3, or principal component number 3. I seem to be okay with this, or I shouldn't say I am okay with this. Now, what if we use 6 clusters? I'm going to try to get through this quickly. This is what we get. We draw lines around this stuff. So we have cluster here, here, here. This one's a little bit more difficult to draw. Yeah, I mean, just from looking at this, I would think 23 and 24 should be joined together, but they're not. Look at number 2. Maybe 6 clusters isn't appropriate. Now, corresponding to this clustering method, the nearest neighbor method, this seems to make some sense. But then when we look at it in one of these plots, I don't think that this clustering method is actually finding the true clusters. Let's compare this to when we did the bubble plot here. Why was 2 separated from the rest? Well, we can see. Look at how that bubble is blue and it's really small compared to the other ones that are in red right next to it. That's why this clustering method separated out 2 from from the other ones. But then again, remember this third principal component is really not explaining much variability of the data. And you can look at all this in 3-dimensional as well. So what do you think of 3 clusters? Since we're running out of time, let's just go there. Well, I guess it's just what I already just said. So based upon what I just saw there, if I wanted to stick with this particular clustering method, 3 would be better. Okay, let's see here. So some comments, examine these same principal component plots. Now for, let's say, some of the number of clusters that were ones I did not choose, like 4, 5 clusters. Use that to justify, okay, yeah, that's why I don't think, let's say, 5 clusters is appropriate. And that agrees with, let's say, the hierarchical tree diagram. So do some of this stuff on your own. Now, what if 2 or 3 principal components do not explain as much total variation as desired in these settings? Maybe it only explains, let's say, 50% of the variation. Can you still look at these 2-dimensional, these 3-dimensional plots? Yes. But just realize that you could be missing out on important information. So I would still look at these plots. But what I would also do is do some of these other plots that we have available that can represent these higher dimensions, such as a parallel coordinates plot. So you could do a parallel coordinates plot with the original data, or you could do it with the principal components, just realizing that maybe I shouldn't look at some of those principal components because they're not very meaningful. So for example, this is a plot that I added. We've done this plot before essentially, but not exactly in the same way. So here's the original variables, okay, with 3 clusters where I designate the coloring of the lines corresponding to the cluster. We can see from this plot that, yeah, 3 clusters would be justifiable. Notice how these reds are standing out from the rest. Notice how the greens at times are standing out from the reds, and then other times standing out from the blacks. This is what I want to see if I want to actually use 3 clusters. Very, very important. You could also do this with principal components, but because I know 2 to 3 principal components are justifiable, I don't need 4, I don't need 5, I would ignore this side here. But once again, we can see for principal component number 2, and even a little bit 3, how the green stands out from the black and the red. So that's what we want to see if we think 3 principal components are necessary. Notice for principal component number 1, that really separates out the red. That corresponds to observations 4, I think 15 and 17. The green is 23 and 24. So you can use those plots, and this is what you will need to do at times for your project. So let's briefly talk about the project some more. Sorry, we'll go over a few minutes. So you now have enough background to really get started on the cluster analysis part of the project. Number 1. So use complete linkage, use standardized data values. Now, it would be good practice to use some of these other hierarchical methods on this too, like nearest neighbor, furthest neighbor. Well, I guess that complete linkage is furthest neighbor. The average method, the centroid method. It would be good to do that on your own for practice. But just to help you focus on the project, what you turn in, let's just use the complete linkage furthest neighbor. Part A here. Run H-clus. Tell me which 2 observations are joined first. Give me the corresponding distance that R gives you from H-clus, but I want you to also show me you know how to do the calculation even without H-clus. So we actually did this last time, where we actually found this Euclidean distance between 2 points. Do that here with the standardized, just to show me that you can do it. Part B, do this hierarchical tree diagram. How many clusters are appropriate for the data based upon the diagram alone? So you're going to need to draw some horizontal lines for your data set and justify it. Actually, give me some written justification. Don't just give me the lines. Give me the written justification. Part C, now do a scatter plot of the first two principal components. Include the cluster memberships in an appropriate manner on the plot, like what we just saw. Comment on how well this plot helps you to justify the clusters, just like what we did. Also, do a parallel coordinates plot of the standardized data, not the principal components. Just do it of the data. And just like what we talked about, put the cluster memberships on the plot. Tell me how this helps you separate the stuff out. Then part E. So, take one of the clusters that you have chosen to find. Interpret what it represents in terms of the data. So like with the goblets, we could say, okay, these are all like small goblets that maybe have a small cup. Do a similar thing here. So that's number one. Now, remember that cluster analysis is used in situations where you don't, let's say, have some natural classification of your data. Typically, you don't have like a response variable. So for example, if you remember the place-kicking data set that we had, where we had successes, and we had failures of place kicks, and we had a number of explanatory and independent variables with it. Cluster analysis wouldn't be appropriate for that data set, because we already have the success or failure classification. For some of your data sets, you have something similar. But for a classroom setting like this, it's okay. You can use cluster analysis on it. I'm fine with that. What might be interesting is to see, okay, these clusters are formed. How does this match up with what we actually know what the true groupings are? It's up to you if you want to explore that. But it's okay with me if you have the natural classifications, or if you have the classifications already there. Just apply cluster analysis to all the variables except for obviously the variable that has the classifications. Okay, any questions? Okay, so I'll have my usual office hours. I'm actually going to need to cut it off about half hour into it. Something came up. And next Tuesday we'll continue with cluster analysis. And again, project number 2 is due Friday, November 3rd at 5 p.m. So 1 week from tomorrow. So sorry that we went over a little bit here. Are there any last questions? Okay, that's all for today.